Hey guys, I couldn't make today, obviously, so I made a YouTube video for you to watch. After the or during the video, make sure that you have your notes out, that you are writing down some important things that you might need to keep track of. And after the video, you will have a study island assignment. It is called linear versus nonlinear functions that you should complete hopefully by the end of the period. This is about a 20-minute video. Doesn't take very long to go through these problems. Hopefully you can get it finished by the end of the period. If not, you can work on it during when or at home. Hey guys, we are going to look at linear and nonlinear functions for today. And it's actually a pretty simple lesson. The idea, we just got done talking about comparing linear functions. Remember, linear functions means that they make a line. Nonlinear means that they don't make a line. And the important thing to remember about linear is there's always the same change. When we looked at tables, we looked at how the y's changed compared to the x's change, and it was always the same no matter what. So that's actually where we are going to start on this particular problem. And what I'm going to do is I'm going to run through a study island lesson for you, and um, I'm just going to give you the examples of types of problems that you're going to see, and then I'll let you guys get to work and try it on your own. So this particular one says, select the data points that need to be removed from this table for it to represent a linear function. And if you remember the comparing functions table that we looked at before, we're always looking at the change in the y's over the change in the x's. So let's go ahead and look at that and see what we can discover here. So these y's, to go from -6 to -5, it goes up 1. And these x's, to go from -2 to -3, it goes down 1. So the change in the y's over the change in the x's is 1 over -1, which is -1. Let me put my little negative sign there. I don't like how I wrote that, so let me change that real quick. So equals -1. All right, let's look at the next one. Let me see about changing color here. So to go from -5 to 1, that's going up 6. And from -3 to 0, that's going up 3. So if I look at my y's compared to my x's, 6 over 3 equals 2. So right now we don't have a linear relationship because the rates of change are different. So we're going to continue on with this process because once again it says find the ones that need to be removed to make it linear. So we're going to see which is going to be right and which is going to be wrong here. Let's go green now. So to go from 1 to 7, the y's are going up 6 and the x's are going up 3. And 6 over 3, once again, is 2. So that's good, all right, because that matches this other two. So what it seems to be right now is we're going to have to get rid of the -2, -6. All right, let's continue on here. So to go from 7 to 15, we're going up 8. And to go from 3 to 7, we're going up 4. And 8 over 4, that equals 2. So that's good. Those points are good. Let's go from 15 to 18. We're going up 3. And from 7 to 8, we're going up 1. So 3 over 1, when we look at the y's over x's, that equals 3. So that means this point we're going to have to get rid of. So let's not consider that point. Let's go straight from that 715 to the 1225. All right, let me grab a new color up here. So since we eliminated 818, let's go from 15 to 25. So that's going up 10. And from 7 to 12, that's going up 5. And 10 divided by 5 is 2. So that's good. And then the next one, 25 to 51, that's going up 26. 12 to 25, that goes up 13. So 12 or 26 over 13, that equals 2. So there's only those 2 points that we are going to have to get rid of. So what we would select here is -2, -6, and the 818. Those are the two that make it nonlinear. And moving on to the next one. All right. Carrie drew some nonlinear graphs from real-world situations or scenarios. Which of the following scenarios could she have drawn a graph for? All right. So what we're trying to identify are which are the non-linear graphs. All right. So remember, linear means everything is going up the same amount over and over and over again. So what we're looking for are the ones that don't go up the same amount over and over and over again. All right, so a window washer determines his horizontal distance from a 40-foot flagpole when washing the windows on one side of a 40-foot building to be 500 feet. Let's draw a picture. So he's got a horizontal distance. So horizontal distance is going left and right, kind of like that. All right, and his horizontal distance from a 40-foot flagpole. So this is 40 feet here. Just pretend that's a flag. On the side of, hold on, the window's on one side of a 40-foot building to be 500 feet. So he's also on a 40-foot building. We're gonna have some fun. Draw some windows here. All right, so here's my building. So his horizontal distance is 500 feet here. So the window washer himself is going to be up on this building, right? He's washing these windows. Scrub-a-dub-dub. All right, so he's washing that window, and he's 500 feet away from that flagpole. All right, then he comes down. He's washing this little window here. All right, he's still 500 feet away, even though he may have dropped down a little bit. All right, if he comes down and washes the windows here, he's still 500 feet away from this flagpole. All right, so even though his vertical height might be changing, his horizontal height is always going to be staying the same. So the change in the y's compared to the change in the x is always 500 feet. All right, it's always going to be the same. So this is a linear situation. If I kind of look at an x and y kind of thing here, all right, so let's say he's 40 feet high on that building. All right, he's at 500 feet. Say he's 30 feet high on that building. He's at 500 feet. If he's 20 feet high at that building, he's 500 feet away. And if we look at the y's over the x's, like we do over and over and over again, all right, our change in y is 0. Our change in y is 0. Our change in x is going down 10, going down 10. It's always 0 over some kind of number. Doesn't matter, which is always going to be 0. So that's, since that rate of change is the same, it's going to be a linear function. So we're not going to select that one. That's linear, not nonlinear. All right. So while I'm erasing this, I'm going to try to read at the same time. So a beetle population first recorded at 10,000 has been declining over the years due to a pesticide. All right, so it's decreasing. Each year, there are half as many beetles as the year before. So let's think about that for a second. I'm going to draw kind of another table. So my x's is going to be the time. So at year 0, they started at 10,000. And then at year 1, it went to 5,000 because it was half as much. At year 2, it was half of that at 2,500. All right. Now, our x's, they're going up by ones each time. So that's good. We got a pattern there. But our y's, this goes down by 5,000. And this goes down by 2,500. Non-linear. All right. So now let's look at machine. Actually, first of all, let's select this one because we know that that's nonlinear, as we just discovered. So machine can bottle 1,800 bottles of soda every hour. And right away, I know this is a linear situation because it's going up the same amount every time. It's going up 1,800 bottles of soda every hour. I like looking at this table just to show how it's linear. So at hour 0, they made no bottles. After 1 hour, they have 1,800. After 2 hours, they're up to 3,600. And what we'll notice is this nice pattern. We're going up 1,800, and then we go up another 1,800 for the Y's, and the X's are going up 1 both times. So we've got that similar rate of change. 1,800 over 1, 1,800 bottles per hour, so it makes sense. So we're not selecting that one. That is a linear situation. All right, and the last one, a frog population, which started at 2, doubles every 3 weeks. I know this is going to be nonlinear. This is very similar to the beetle population. Instead of going by halves, it's doubling. I'm going to go to the table again real quick. So at year 0, it started at 2. And at year 1, or after 3 weeks, so we'll say this is 1 3-week period, it doubled. So it went up to 4. After the second 3-week period, it doubled again and goes to 8. So if I look at my x's are going up 1. I got a clear pattern. All right. My y's are, there's a pattern here, but the thing that ruins it for being linear is it's not going up the same amount each time. So when I look at the y's over the x's, I've got 2 over 1, which equals 2. And then I've got 4 over 1, which equals 4, which makes it non-linear. All right. Same idea. We're trying to find the non-linear function. So Olivia knitted 2 scarves each day this week. 2 one day, 2 the next day, 2 the next day. All right. So she's going up by 2 every day. That's a linear situation. Ken runs a tutoring service. He charges a fee of $30 per hour. All right. So it's going up $30 every hour. So it's going up the same amount over and over again. That's linear. Greg is driving to another state. He drives 135 miles every 2 hours. So every 2 hours, it's going up 135 miles. Goes another 2 hours, increases 135 miles. So it's the same over and over again, which leads us to the last one. Linda has $1,500 in her bank account that pays 3% annual interest. All right, and this is interesting, because people look at this sometimes and they, okay, she gets 3% after 1 year, and then she gets 3% the next year, and 3% the next year, and you might think that, well, that sounds linear. It's the same over and over again. But what you have to realize is when she has $1,500 and she earns 3% of that, I'll grab a calculator real quick. So 1,500 times 0.03, that's $45. Okay. So now in her bank account, she has $1,545. And if I take $1,545 and multiply that by a percentage, now she earns $46.35. So 1 year it went up $45. The next year, it goes up $46.35, and that amount is going to keep increasing over and over and over again. In fact, the year after that, it's going to go up $47.74. All right, so that is the nonlinear situation. All right, next question. Which of the following best describes the equation below? It's linear. And the easy reason for that, it matches y equals mx plus b, which we talked about a lot last week. So linear. So next question, a factory that manufactures basketballs spends $7 in each basketball that it produces. Is this linear or nonlinear? So if you think about it, one basketball costs $7. And I'm going to do the quick table comparison again. I should start at zero. 0 basketballs cost $0. One basketball costs 7. 2 basketballs is going to cost 14. 3 is 21. All right, we don't really have to look at the table to realize it's going up the same amount every single time. All right, but I like to look at the change in the y's compared to the change in the x's. In this case, the x's are going up 1, up 1, up 1. So it's always 7 over 1, no matter what. 7 over 1, 7 over 1, 7 over 1. So this is a linear situation. Here's another table. We have to take a look. And we have to kind of check everything here just to make sure that it's linear, because it only takes one to mess it up. So from 5 to 25, going up 20, and the x's are going up 1. So right now we got 20 over 1, which equals 20. To go from 25 to 125, it's going up 100, but the x's are only going up 1. So now we're looking at 100 over 1, which is obviously 100. Then it goes up 500 compared to 1 for the x. And then I don't even know what that number is, but it's pretty large. So it's definitely a non-linear situation. Nothing is ever the same when it comes to the rate of change. So that's non-linear. Taking a look at this one. Can we make this look like y equals mx plus b? So we got a little simplifying to do. First thing, we've got that exponent, and 15 squared is just 225. So when we look at this, we're thinking, okay, this is y equals x over 2 minus 225. So is this y equals mx plus b? Because if we can make an equation look like y equals mx plus b, that means it's linear. And right now we kind of got the plus b. All right, we got the number by itself. But do we have a number multiplied by x? All right, and right now it looks like we got a number divided by x. Does that count? And the answer is yes. Multiplication and division are essentially the same thing. They're inverse operations of each other. They can kind of be considered the same type of operation. And here's kind of why. X divided by 2 is saying the same exact thing as taking 1/2 of x. So if you divide something into 2, you're taking half of it. So now when I look at this as, do I have a number that I can multiply by x here? That's at 1/2. So that equals my m. So indeed, this equation can be put into y equals mx plus b form, therefore making it linear. Okay, another table. So let's quickly go through this one. Y's, that goes up 1, while the x is going up 1. So right now our rate of change is 1. But then we go up 7, while the x is still only going up 1. And then we go up from -6 to 13, that's going up 19, while x is still only going up 1. So our rate of change is different. The rate of change changes, which means this is a non-linear situation. All right, one more to go here. Which one represents a linear function? Hopefully you look at these graphs and you see they're both lines. All right, so both w and x are linear functions. All right, so as long as they're lines, it's going to be linear. Nonlinear could look something like that. All right, it doesn't make a line. That's not a line. I got two parts of lines, but it's got to be one continuous line the whole time. All right, so what we're going to look at is this study island lesson called linear versus nonlinear functions. All right, that's going to be your assignment to get on after this. If you struggle or you remember or can't remember something, go back and look at this video. Everybody has a link to this video in your email. You can do that. Good luck, and hopefully I'll see you guys soon.